Hi guys, I'm back. Don't know how much I'm going to get over on this one. This will be kind of like the second part of dealing with some of that math and stuff. One thing I left off from the last time I wanted to talk about just a little bit is, again, playing with this and the scientific notation that goes along with it. I said something about, capacitors, and how, if you're lucky you buy a capacitor, you'll have, it'll sit there and tell you it's a 0.01 microfarad. But sometimes, some of them you buy, they'll have like 103 or 153 or 154 or 152 or 102 or things of this nature. And I wanted to kind of go over exactly what that means and how you figure it out. All capacitors are based, when they're just got a number like that, they're all based from picofarads. So we're down in here the 10 to the minus 12 range. Now we'll take 103 just as an example, but you can use any number. If you see a 103 on a capacitor, that's the same thing as 10,000 picofarads. 1 and 0 is your numbers, and then 3 for 3 zeros. Now if it was 104, it'd be 100,000 picofarads. You'd have 4 zeros. If it was 102, you'd just have 2 zeros, so it'd be 1,000 picofarads. Now 10,000, if we look, comes out to be 10 to the 4th. So this is the same thing as 1 times 10 to the 4th picofarads. Well, what's picofarads? Well, picofarads, we know, equals 10 to the minus 12th. If we look at this, and if we, in our own little minds, because that's really what it is, this is 1 times 10 to the 4th picofarads. So it's actually the same thing as 1 times 10 to the 4th times picofarads, or times 10 to the minus 12th. So I could go like this and multiply that to 10 to the minus 12. Our 1 will come down, take that times, now we just add those two together. So 4 added to a negative 12 will give us a negative 8. That there, okay, that gives you something. That's the farads, but what does that actually mean? Well, we go back to our chart and we kind of look at this and we go, well, 10 to the minus 8 sits in between micro and nano. So what is it? Well, 10 to the minus 8 is one step up. So really, if I want to rewrite this and have it in nanofarads, it's 10 times 10 to the minus 8, or minus 9, excuse me, which is the same thing as 10 nanofarads. But your capacitors or your schematic may not say anything about nanofarads. It's probably going to have micro or micro, which is pico. So it's either going to be micro or micro or picofarads. How can I change this to something micro? Well, the nearest micro is 10 to the minus 6. So how do I get up there? Well, when you move up the scale, you move the number to the right, add zeros in front of it, but you're actually moving the decimal point to the left. So this here, minus 10, if I want to make that minus 6 for microfarads, then I got to move over that decimal point a couple places. So then I'm going to have a 0.01 there instead to get it to 10 to the minus 6. Remember, the big thing to remember, move up, decimal point left. Move down, decimal point right. And it moves the number of places you need to move. And your number of places will be how many times you got to move it. You know, from minus 8 to minus 6 is 2. I moved left, then 2 points. So now that's a 0.01 microfarad. So in other words, a 103 is a 0.01 microfarad. A 104, if you start really looking, would be, we'd get rid of this 0 and the decimal point would be here. A 104 would be a 0.1 microfarad. I know it may seem like quite a bit of operation I just did here, but after a little while you'll get used to it. You'll get where you can actually just recognize the number. You'll get used to the idea that, oh, it's a 104, that's 0.1. And a 103 is 0.01. And a 102 is 0.001. Or whatever. If it's a 153, then it's a 0.15 or 0.015 microfarad, actually. But I just kind of wanted to go over that. Now, if you have any questions about it, we'll do a lot more on it. I'm still going to do something on components, because there's, especially capacitors, there's a lot of different color codings to them, a lot of different types. You got tubular ceramic capacitors, a little tube with a couple wires on it, wrapped on there, and it's got all these little dots of color. You've got some ceramics that actually use a dotted color mechanism. You've got some ceramic capacitors that look like a resistor, except they don't have enough stripes, and but they use stripes. And you know, of course, you got your 103, 102, 152, 153, 154, and or you know, whatever numbers it's on there. So there's various methods and stuff. Now I want to talk about, we've talked about the resonance formula, and see if I can move this. Oh, jumpy. Sorry if it's a little jumpy there, I didn't mean for it to be that way. And I'll try to gear in on that a little bit. Okay, but we've talked about the our resonance formula in the past about F equals 1 over 2 pi LC, the square root of. There's a couple other formulas that are kind of important when you're dealing with inductors and capacitors, and one of them is kind of important when it comes to, well, they're both important, but one will be used in another formula that deals with resonance. I don't know why I keep saying resonance, but it's X sub L and X sub C. Now, what these mean, basically, or what they are, X sub L is inductive reactance, X sub C is in capacitive reactance. Basically what they are is a measure of both, either an inductor as inductive reactance or capacitors and capacitive reactance. It's a measure in ohmage, is the values that they use, of the resistance that either an inductor or capacitor has to change. One of the things that you need to, well, one thing about it, this is dealing with AC circuits, and an AC signal, you know, sine wave or whatever, it's always changing, and either the capacitor or inductor, either one of them, don't like change. They want things steady state. So what these formulas do is figure out how much resistance that they have to that change. So why does that happen? And how, well, before we get to the whys, something I want you to pay attention to, and it's a mathematical terms, but the X sub L, or inductive reactance formula, equals 2 pi FL. X sub L, now 2 pi is a constant. We've already dealt with that. Like I said, in any type of math that you may ever do with 2 pi on these formulas, just think of it as 6.28. Just write that in there. Pi is 3.14. 2 times that is 6.28. And for the pure math guys out there that ever sees this, yes, I do know that pi goes on forever and never repeats. And so, but for what we're doing, 2 decimal points, 2 places past the decimal point is perfectly fine. So for 2 pi you can use 6.28. Okay? Not a problem. So don't worry about pi. The 2 variables in here is frequency and inductance. When either one of these go up in value, X sub L goes up in value. If either one of these or both go down in value, X sub L goes down in value, because it's what is known as a direct proportional entity. That's what this formula is. X sub L is directly proportional with respect to F and L. Basically all that means is whatever F and L does, if they go up, it goes up. If they go down, it goes down. And that's one thing I want you to really pay attention to on this. On the other one, X sub C, we have a 1 over. It operates opposite. If F or C or both go up, X sub C goes down. If F and C go down, X sub C go up. So if either one or both go up, this goes down. If either one of these two go down, he goes up. And it's called indirectly proportional, or indirectly proportionality. Being that this 1 is over the F and C here, then whatever they do as far as up or down in their value and changes is indirectly proportional to this. It's opposite. So X sub C will do just the opposite of what these guys are doing. And that's kind of important, and it happens in here too, in this formula. Your frequency will change indirectly proportional to what your inductor and capacitor is doing. Now, most radios and most signal generators have fixed inductors or fixed coils, and you tune the radio by changing the capacitance. You rotate the capacitor. Now, yes, there are some radios that are inductive tuned, and in that case the capacitance is fixed and the inductor changes. But if you're working with this formula and you have that indirect proportionality there, the inductor is fixed and the capacitor is what's churning. When the variable capacitor, your tuning capacitor, is fully closed, it's got maximum capacitance. So at this point, when it's completely closed, it has maximum capacitance the frequency is the lowest for the radio. When you open this, this is fully open. It's totally unmeshed. No meshing whatsoever. These are completely out of these, so that this is the least amount of capacitance that this thing can handle, or has. At that point, that's the highest frequency that radio can tune. So the next time you're ever messing with a radio and your alignment instructions are rather vague, and they just tell you to tune to 550, the low point on the band, then on AM band or whatever band, but the radio is out of the cabinet, you don't have a dial or anything that tells you where that's at, you'll know that that's the low end, that's the lowest frequency. So that's going to be when the tuning condenser is fully meshed, because of this formula. So then proportionalities, I wanted you to quite understand a little bit. Now we'll get into what happens with these two and why they do what they do, and why these formulas exist. Okay, let's look at the inductor first. Now, when you put an AC signal into an inductor, then it starts charging up. Now, something I need to point out real quick about electricity, and I'm trying to find something that I can use. Okay, here we go. You got a piece of wire. If I put a voltage through this, okay, and say it's DC, right off the bat, we'll start with DC. If I put a DC voltage through this wire, just a straight piece of wire, I hook it to, I don't care, 9-volt battery, whatever, it don't matter. Okay, this wire will actually produce a magnetic field around it. It'll be in a circle like this, looking like this, and it'll produce. Now, there are things called the right hand and left hand rules. They'll tell you which direction that magnetic field's rotating to the flow of electricity. I'm not going to get into that today on that exactly, because it has nothing to do with fully with the explanation of this. But anytime you put a voltage to a wire, or if you coil it up like a coil, either way it builds a magnetic field. A magnetic field will build around it, because electricity and magnetism cannot be separated. They're always constantly connected. Now, if you got a straight piece of wire, you got a fairly weak magnetic field. If you coil the wire up, then that magnetic field strengthens, because each one of those little circles of magnetic fields around the wire all start adding together and then build a large magnetic field. Now, the same principle works in the opposite direction. Say that this is a well, it is actually, there's a magnet here. If I got a piece of wire and I start moving the magnet back and forth on it, I've got to keep it in motion. Now, either I can move the wire or I can move the magnet. Either way, this magnetic field that's around this magnet will cut across this wire, literally cutting through it. The lines of force of magnetism cuts through the wire as I move that magnet, and in turn will produce electricity in the wire. There'll be a flow of current because of that. So you put a battery or put electricity to a wire, it produces a magnetic field. If you move a magnet on a wire, as long as it's in motion, or the wire's in motion relative to the magnet, you produce electricity. Now, it looks like with my time, all I'm going to get to is just the X sub L right now, and we'll do the X sub C on the next one. That happening, you got a coil and we're going to back this off a little bit so you can kind of see what's going on here. I got a coil right here. Hook it to AC generator. That's all that means. It's supposed to be kind of like a sine wave. I'm not an artist. Okay. Now, let's see if I can do this. Yeah, close. Now, I have a sine wave. At some point, it's going to start from 0 and it's going to start building up, heading upwards to the positive end. So at some point, I'm going to have a positive, and then at the other end, it's going to be negative. So in this top part here, every time, all through that, it's going to be positive one end and negative on the other. Now, I'm starting to apply a voltage to the coil because the sine wave is advancing above 0. Alright, well, what that does, the coil starts building a magnetic field. Now, I guess I said something about left hand, right hand rules don't mount to this, but anyway, actually, due to those rules, as it starts building a magnetic field, that magnetic field is expanding. As it expands, it cuts across the coil, the wires in the coil. In turn, that actually induces what they call a counter EMF, or counter voltage, because the field is moving with respect to the wires, but it's producing a voltage in the opposite direction because of the way it's moving. So it's trying to produce this. Well, you ever tried hooking two batteries up and let them fight each other? They don't like it. This one here, the red, the counter EMF, is opposing the other one. Now, what happens is a strange little event, and if I can draw it, I'll try to draw it. This is voltage, we'll put E, and the little red mark, we'll put I, that's current. What happens is the voltage starts building first, but being this counter EMF is in there, the current can't flow because it's canceling itself out. The current doesn't start flowing until approximately 90 degrees later. Then it'll start flowing, and that's generally about the time that the EMF or the voltage is at max. At that point, because when it hits max, it stops moving. The field stops moving. Everything stops moving. Now the current can start flowing. Now the current will continue to increase because now that voltage on this generator is now dropping. As it drops, the field starts collapsing. And due to that collapse and everything, now this is dropping at the same rate as the counter EMF is building. So, and the direction will be the same. So I start building more and more current flow as that voltage goes down. When the voltage hits at this point at 0, I peak my current. And then it starts going negative. And the same thing happens on the negative side as happened on the positive side. And then we get back to here, and then we just redo the cycle. But due to this opposition to current flow, and due to the counter EMF and everything else, that's how it's resisting change. That actually reduced the current just a little bit. There's a loss of energy, and that's reflected back into this formula as a resistance that we call inductive reactance, and it's a resistance to the change to this AC. And I hope I've explained that extremely well. Now, I'll leave this on here, and in the next video we'll do what's happening with the capacitor. And then I'll show you a way to remember this and what's happening here. But in this case, in an inductor, it is said that voltage leads current. And it does by 90 degrees. Well, in perfect world it's 90 degrees. It's not exactly 90 degrees, but due to resistances and everything else that's in the wires and everything else, we'll kind of adjust this and change it just a little bit. But it's pretty darn close. So on the next video, we'll go over the capacitors, and it's capacitive reactance, and then we'll put this together, and then I'll show you how this formula came about, and we'll see where we're at there. So until the next time, thank you for all your wonderful comments, and I will answer them online. I got me a new keyboard and things seem to be improving that way, so just give me a little bit of time. I will get back to you. I did want to say one thing so I didn't have to write all of it out. Art, I am planning to put the schematic and a parts list on that Google Drive so everybody can get to it, but not yet, because I want to make sure that that ain't a finalized schematic. Until that thing is actually operating and operating as best it can, then we'll have a finalized schematic, and that'll be when I'll put it on. So anyway, until next time, guys, thanks for watching and in your comments, and I hope this helps, and we'll be doing another one after this one. Thank you.